Lattice structure. This structure is widely used in digital speech processing and adaptive filters. To get to the full discussion, first consider a first-order FIR filter of type y of n being equal to h of 0 x of n plus h1 x of n minus 1, okay, which is equal to x of n plus alpha 1 of 1 times x of n minus 1. Now, here you see the structure, okay, delay k1 x of n minus 1 and f1, which is equal to the output y of n, and g1 of n. FIR filter with lattice structure. If we assume that h of 0 is equal to 1, the output y of n can be computed from the structure shown in figure. f1 of n will be equal to x of n plus k1 times x of n minus 1. g1 of n will be equal to k1 times x of n plus x of n minus 1. Alpha 1 of 1 will be equal to k1, and y of n will be equal to f1 of n. The parameter k1 is called reflection coefficient. For a stable filter, the relation abs of k1 is equal to or less than 1 holds. Now, FIR filter with lattice structure having two cascaded parts. Very simply, just add the first part to the end of it. You'll have two parts, and 3 and 4 and 5. Okay? Again, K1, F1, G1, and delay K2, K2, F2, and G2. Now, figure 9.8 shows an FIR filter with lattice structure having two cascaded parts. So, G2 is equal to K2 times F1 of n plus G1 of n minus 1, and F2 is equal to F1 of n plus K2 times G1 of n minus 1. And this part for you, and y of n will be equal to f2 of n, which is equal to x of n plus alpha 2 of 1 times x of n minus 1 plus alpha 2 of 2 times x of n minus 2, where k is equal to alpha 2 of 2 and k1 is equal to alpha 2 of 1 over 1 plus alpha 2 of 2. The above relation can be extended to an n-degree FIR filter. For this purpose, reflection coefficients must be calculated repeatedly. If the degree of the FIR filter is equal to n, then it can be written that if m of n will be equal to f m minus 1 of n plus km times gm minus 1 of m, and gm of n is equal to km times fm minus 1 of m plus gm minus 1 of m, where m varies from 1 up to capital N minus 1. If both the initial values of fm of n and gm of n are equal to k0 times x of n, then the output of m minus 1 step of the corresponding lattice filter will be equal to the output of the FIR filter with degree m minus 1, that is, f0 of n is equal to g0 of n, which is equal to k0 times x of n, and y of n will be equal to fm minus 1 of n. Considering the structure of the direct form of FIR filter in the form h of z without reading the nature of it, okay, and considering capital M minus 1 of z being equal to 1 plus sigma m from 1 up to capital N minus 1 alpha n minus 1 of m, and having alpha n minus 1 of m being equal to bm over b0, it is possible to find the coefficients of the lattice filter in the following iterative way. K0 is equal to B0, Ka minus 1 will be equal to alpha n minus 1 of n minus 1, and Jm of z will be equal to z to the power of minus m times am of z minus 1. And am minus 1 of z is equal to am of z minus km times jm of z over 1 minus km to the power of 2, or km squared. And km is equal to alpha m of m. The above algorithm will not work for f's of km being equal to 1. As a result, for FIR filters with linear phase, a lattice structure cannot be used because B0 is equal to f's of Bn minus 1. So we will have Km minus 1 f's is equal to f's of alpha n minus 1 of n minus 1, which is equal to Bn minus 1 over B0 f's, which is equal to 1. That's why. Another name of this method is Durbin-Levinson iterative algorithm. In a similar way, we can obtain the network structure for an IIR filter with a phase equal to 1 in the transfer function all-pole filter. This structure can be seen in figure 9.1. H of z is equal to 1 over 1 plus sigma m from n up to capital N alpha n times z to the power of minus m, which is equal to 1 over a n of z. Okay, IIR filter with lattice structure. Okay, to find the lattice structure coefficients, we use the following relations. K0 being equal to 1, Fn of n, x of n, Fm minus 1 of n is equal to Fm of n minus Km times Gm minus 1 of n minus 1, and Gm of n is equal to Km times Fm minus 1 of n plus Gm minus 1 of n minus 1, and y of n will be equal to f0 of n, which is equal to g0 of n. Now, IIR filter with lattice ladder structure. Okay? The correct name of this structure for the IIR filter is lattice ladder. Compared to the direct form structures, this structure is less sensitive to the quantization errors of the coefficients. Meanwhile, the transfer function of the filter is n greater than or equal to capital M. So, h of z is equal to summation k from 0 up to capital M bm times z minus k over 1 plus sigma k from 0 up to capital N bn z minus k, having a numerator and denominator called bm and an. Yn is equal to sigma m from 0 up to capital M vm times gm of n. And I don't want to read the rest because it's a huge writing. If you are interested, you may find them later in details. No.